So welcome back to the session, our session. So today we'll be talking about a little bit about group manipulations. And this is quite critical or useful when you have data in any format and you want to basically play with the data by grouping them either by rows or by columns on certain categories. You'll see some of these options. So before going with the group manipulation part, we discussed previously like functions and some of the other part of iterations and anything, for loops and while loops and other things. Any question from that part you have? Okay, if not, then I'll go ahead and then basically today we'll just look around grouping the values by rows and columns, and then trying to do some sort of a calculations on those grouped values. And we'll look into some of the functions that comes from apply family. And then we'll look about aggregate some functions from dplyr. And finally, we'll just one function I will just introduce, which I don't think you possibly would be using a lot, but it's good to know. So that's a function is fread from data.table package. So going ahead, so yeah, okay. So just to basically let me first create an object. In this case, I'm just going to create a matrix. So as we know, the matrix is basically a two-dimensional object which has rows and columns, and the type of data inside a matrix of a single type. It's not can't be of a mixed type. If there is a mixed type, the data get coerced into one particular format based on that coercion rule which we saw. So let's say this is the matrix which has rows and columns, and we want to perform some sort of a manipulation or some sort of a calculation on the row wise. So all the values in a single row, we pick them up and do some calculation with those, or pick up the values either column wise, whatever our need is based on that. So what we will see is first we'll start looking into one particular function from apply called apply, and the apply takes three different arguments. First, the first argument is the data object. Second argument is whether we want to perform the manipulation across rows or across columns. So if you specify one, that basically means by rows, and two is by columns. And the third argument is what kind of function, what kind of manipulation we want to do once we have grouped the values by either rows or column based on the second parameter. So those are the three parameters for that one. So so the first function is apply. So let's use apply function. First thing is to specify the object. So we'll take the matrix A1. And then we would have to specify whether we want to do that, whatever we want to do, the calculations or function. We would like to do it by rows or we want to do by columns. So first let's pick up rows. So we say comma one specify rows, and then we simply can say sum. And we want to sum up all the values for each particular row. So essentially the first is data frame. Second, we are going to perform function by rows. Each rows, take all the values by rows. And then for each row, apply some function for those particular values. So he's going to add up all the values from the first row, then the second row and third row, and the sum of each row is then printed out separately. And you can see that those are the values that prints out by sum. Similarly, if you want to print out the sum by columns, change the second value to 2, and then basically then we specify, okay, on the matrix A1, perform group them by columns, and then once you're grouped, pick up the values of the columns, sum them up, and this is the value which we get once we start doing by column wise. Similarly, there are other functions as well. So instead of just let's say sum, we can also use mean. Mean is calculates the mean of all those values across the columns. It basically sums up all the values and then calculates the mean of those values, and those are the means. And the same can be done even across rows as well. So I think you get what I'm getting it as basically we are grouping the value based on the rows and based on the columns, and then trying to perform some sort of a calculation on those ones. In most of the bioinformatics packages we use, these functions are by default either part of some function already your function you're using. So you may not be doing explicitly these things, but it's good to know that these functions can be operated. Sometimes you may have to, there may be a need that you need to do in a group the values by rows or columns and then perform some sort of calculation or a function, run a function over those particular values. The most common you see values by groups, by rows, is like when you're trying to do heat map. So when you generate a certain transcription profile, you have like expression data from 10 or 20 different samples, and you want to do a heat map of those ones. In those scenarios, mostly what you do is you scale your data across rows. So you scale the data. That basically means you normalize your data in such a way that the mean is 0, and then basically the standard deviation is 1. So you scale up that particular data, and then you have G-scores for each of the values in your row, and that's basically used for putting heat map. Column-wise manipulation you can think of in terms of, let's say you have 10 or 12 different samples in columns, and you want to normalize those reads. So for example, these are the values across 6. If you think about 6 different samples, and because of the high read depth, the last column got sequenced too high, and then less, and then less. So before we start doing any sort of, let's say, if you consider rows as our genes and want to do some sort of a statistical analysis, we want to normalize the data with respect to the read depth. And in that scenario, then we have to first find out, okay, how much is the read depth across each of the different samples, and each sample is represented in a column. So we sum up the values across column, and then basically from there we go ahead and do some sort of a normalization. There are different ways of normalizing data, but the simplest is like scaling it down. So you basically reduce the values in which you have high reads to match the reads for the lowest sample with the lowest count. So, but there are different other ways in which you can do it. But these are 2 examples I'm giving where you would like to group your data either by rows or either by columns. Now, then one of the scenario is sometimes you may end up encountering a matrix which is of particularly this type. So in this one, there's nothing. What I've done is in one of the rows, I have inserted NA inside that one. So now the thing is, if you now run the same basically functions, those functions will explicitly tell, if you do by rows, then the third row values are NA because it cannot sum up NAs. And if you do by columns, and all the middle ones, like from column 2 to 5, that has been assigned, they cannot be summed up because of the NA value, or the mean cannot be calculated because of presence of the NA values. So in that scenario, what it does, it just prints out NA. But it's quite common that if you whichever data you're playing with, sometimes they have missing values. So there is a way around that one. And that's what it is in line number 43. We are actually executing the same code what we had before, except that one extra parameter we are specifying. So we are saying matrix A1, which is same as previous. We are doing it by rows, and we are calculating sum. The only thing we are adding is na.rm equals to true, which basically means remove na. It's not like remove na from the matrix, but it doesn't take those na values in account, but then sums up those values. And in this case, you will not get an na, but it will return up the values. So this 31, which was initially was na, when we didn't have this parameter specified, was na, now the value is 31. The same thing can be done if you have values, or if you want to do by columns. And essentially now, instead of having NA in the columns from 2 to 5, we have now values corresponding to those particular columns. So this is some of the tricks you can use. One of the things you need to be aware is that so for example, if I've calculated this mean, and then I should be aware while I'm using this data downstream that there were NA in these values, and the mean is across only like 4 values, not 5. If let's say 5 values are really critical, or somehow it can affect the downstream analysis, I need to be aware of those particular facts. Sometimes the NAs get imputed by values. So those values could be the mean of the whole matrix, or sometimes the lowest value, depending upon what kind of analysis we are doing. So those values get imputed, and then you calculate mean from there. All right, so these are the above couple of apply functions, when I use the functions which I am using, like sum and mean, are pretty standard functions that comes from base R. If there is any other kind of function you want to apply, you can use that as well. And let's say I want to have my own function which I want to apply on the data, either by rows or either by column, I can do that as well. So for example, I'm just going to recreate that matrix A1 again. So let me clear up my screen. So this is the matrix on which what I want to do is want to calculate variance of the data across the, you can say basically across rows or columns, I don't care. But let's say if I have certain number of values, I write a function var underscore f, which basically calculates the variance of the data which is supplied in a vector, a certain set of numbers it takes, and then calculate variance from that particular data set. So that is the function that is is able to perform that operation and gives me the variance. I can, rather than using like mean and sum from the base R, I can use this function which I have written with the apply function, and that can be done basically copy and paste and then explain. So yeah, apply. Again, the first is the data object, that is the matrix. Then I want to do it by rows. And what I specify is fun is for function. Function is equals to var underscore f. And this is the function which I wrote here. So in this way, I can write another function, and the function using which I want to do a very specific kind of analysis, I can actually specify that. Then when apply function gets executed, it picks up the values by rows, all groups the values by rows, and then supply those values to the function which I have specified, and it operates on those ones and basically executes the function. So I didn't execute the function, so the function doesn't exist. That's what it basically tells me. Sorry. Go back and execute it. Now it actually ended up calculating the variance across all the rows. Okay. So this is basically working over the matrix. So the input data in this case is particularly matrix, but we can have data types of other types as well. You can have lists, and we can have vectors, and how we would like to do on those ones. So a couple of other apply functions I will talk about now. One of them is lapply, then an sapply. We'll talk, and in both cases, the output is a little bit different with respect to each other. Right, so let's say I have a list, my list. This is the list which I have created. Let's see what this object has. So it has 3 different entries. The first entry is a matrix with 4 columns and 4 rows. And second is again a matrix with 4 by 4. And then I have a vector for certain element values. Now in this one, what I can do is I can operate over all individually, perform some function on A, then B, and then C independently and get their output. And since the function is apply on list, the function I'm going to use is lapply. And what my object is my underscore list. In this case, there is no rows and columns, so there is no second argument saying comma 1 and comma 2. But finally, we specify what is the function we would like to perform on each element. So I can say, let's say sum. So what essentially it does, it calculates the sum of all the values here and prints out this one, sum of all values for the second element, prints out, and the sum of all the elements in the third one, and prints it out, the values out here. The output of lapply is again a list. So you can see that the list which I created has a $A, the first element, $B, second element, $C, the third element. Same is the output is $A, $B, $C. So the output is also a list. Sometimes it's much more useful that if you can get this output rather than having in a list, what if you get it in the form of a vector? That sometimes is quite useful. So in that case, the function you can use is called sapply. Sapply my list, okay, my list, comma sum. And if we execute now, rather than outputting as a basically as a list, it outputs as a vector. So this is a vector of 3 elements, and A, B, C are the name of each element. So if you remember, when we're creating vectors initially, there was a function called names that can be used to assign names to each of the vector elements that can be done. So that's essentially that has happened here. So The output is a vector, and each element has a corresponding name that specify, okay, 136 corresponds to the value in the list whose name is A, and B, and then C. So that's how pretty much the whole thing is being done. S-apply can also be applied over, let's say, vectors. So let's say this is a vector, fruits. Fruits is a vector which holds the name of certain character strings, essentially 5 different fruit names. And we can apply a function called S-apply. And we get S-apply, the object is fruits. And what we want to do, let's say we want to calculate number of characters. And it tells you how many characters are there in each one of them, 5. So the function that we're going to apply has to be really executable over the data type. That has to be made sure, because we like to do like sum or mean. We can't calculate mean of an apple or mean of a pear. That's not possible because the values are string type. So that function should be able to execute over the data type that is we are supplying while using the apply function. So that's really key. The other one is apply function. So apply function, what it does, it can take 2 lists and map the items position wise. So let's look at 2 lists here. F list, which is the first list, that has 4 objects. The objects are, the first one is a vector, second one is again a vector. No, the first one is so the first one was so the first one was a vector. The second one is a matrix from 1 to 25, and the number of columns are 25. So it's a single row matrix. And then we have P10, which is a single value or variable number holding the value 10. And then we have a vector holding value 1 to 5. Now let's the second list here is S list. And if you look again, there's S list has, first one is a matrix, second is a vector, third is a matrix, and fourth is again a sort of a vector for values 1 to 5. So we can now, what list does, or apply function does, is it maps the first element of one list with the first element of the other list. It will going to bring them together and going to perform the function, whatever we are asking it to do. Okay, and then it takes the second element of the first list and second element of second one, then it's going to do, then the third element, then the fourth element. So it does pretty much brings them pairwise and then try to apply the function over there. So let's, so again, one thing to note is the way these functions are written are now switching over. Now in apply, we are writing the function first, and then I'm going to give the object types later. Whereas before we started with apply, in case of the apply, we first specify the object, then we specify rows and columns, and the third part was actually the function. By the time we reach to lapply and sapply, we have only 2 arguments. Our first argument was the object, which was list, and the second argument was with the function we are applying. Now, when you come like mapply is the other way around. You apply tell the function first, and then basically the 2 objects we are going to be using. So mapply, what it has done is calculated the sum over the first list and the second list. So it took the first element of F list and first element of S list, summed them up, the value is 301. Then it took the second element of F list and second element of S list, summed them up, and the value is 650. Then the third element of F list and third element of S list, summed them up, that's 850. And then finally the last element of F list and S list and summed them up. So that's how the mapply is working over these ones. Now the next one is another function called identical. This is quite crucial. Like, it's good to know about this function. If you have 2 data types and you're trying to compare whether they are exact replica of each other, you can simply say whether those two data types are identical to each other. So here what we are saying is F list identical to S list? So when it's going to find out whether they are identical, it's going to match that match the elements pairwise. So it's going to match the first element of F list with the first element of S list and see if these have exactly the same values, or are there exactly identical objects or identical values in there. Same thing is going to do with the second element, third element, and fourth element. If it is identical, it's going to say true. If it is not identical, it's going to print out false. So it's going to tell us that the first, second, and third elements are false. They're not identical, but the fifth one is true. So if we look at the objects, what we have F list, so, and we look at S list. I'm just reducing the size so we can see it together. So F list, the first element is 10 to 20, whereas in the here it is a matrix. So they're definitely not identical. The second elements, again, is very different for the second elements here. The values are till 25, but this is a vector and this is a matrix. That they are different. The values may be like 1 to 25. Here is also 1 to 25, but this is a matrix. And here it is a vector. So they're not identical. Then we go to here, it's a value 10, whereas here it is a matrix. Again, they're not identical. When we go to the last one, it's a vector of values from 1 to 5. Here also it's a vector of values from 1 to 5. So it says, yeah, this is two are identical. So that's why this is true. And the rest, everything is false. Okay. So if you have two objects, which have, you possibly assume, or basically you're thinking that the data is exactly identical. So for example, if you have a matrix which is in this type, and another vector, you have another matrix which you see on the top of it, the values are exactly the same, but if it returns that it is at false, they're not identical. Most likely the data types are different. So one is maybe having integer values, another maybe those same values are in numeric data format. So the class of objects are, the class of data is different. So though the value looks really the same, but they are, the values are different. So that you have to, so we need to be aware of that. So that both objects which we are comparing has to have the similar kind of data types. If one has integer and another numeric, they're not going to be identical to each other. So even if the values on the face will look like really identical, but they are not. All right. And basically, I can demonstrate that one. So let's say we have an object, we have a vector one, a vector which has values like say 1, 2, 3, and another vector b, c 1, 2, 3. So these are two vectors, a and b. So if you look at a and b, so now let me say as dot numeric a. So I'm going to change the class of A to be numeric, and going to class of B as dot integer. And I think it should be okay. Now let's look at A. Oh, sorry, look at A and then look at B. So they look exactly the same, okay? And if you say identical, A comma B, is going to tell you false. But if you look at A has the exactly same values as B, but they're not identical. They're not identical because A has the data inside A is numeric class, whereas the data in B is actually of integer type. So if you somehow believe that no, there is no way that the two data sets can't be identical, the most likely reason it's not saying that, or basically outputting that identical function output false, because the class of the data is different from each other. So you need to make sure that that's not the case. Any questions here? Okay, if not, then I'm going to talk about some other, so talk about some of the apply, similar kind of, it's not called apply, these are called ply functions, and the ply functions come for a package called plier. And the plier packages takes data into 3 different type formats. So if I want to use the plier, I have to install that package saying install.packages plier. If for example, if you say require plier and it gives you an error that package doesn't exist, that basically means you have to install that particular package. Once you have installed, require plier should be able to okay. So these are basically input data types, the column, and this is the output data types. And these are different functions. So you possibly want to give as a data frame as an input, but want a list as an output, or a vector as an output, or want a data frame as output. For each of these ones, those functions do exist over there. So for example, ddply. So ddply basically means the first letter is basically from the output. What's the output class is? So here the output class is data frame. So you're inputting a data frame. The output is data frame and your input is a data frame. LD apply. output will be a list and input will be a data frame. So if you use LD apply function on a data frame, the output is going to give is a list. So it depends upon what you're looking for. Once you start doing this analysis, there will be a need that sometimes you have a data frame and the output you want a data frame, or sometimes you have a list. Let's say your input is a list, but output you want a data type. Then you simply can say DL apply. So ply stands for the plier package, but the first two letters indicates whether say you're using a data frame output or array output or a list output, and the second one is what is the input of the data. So based on what is your input, you're going to choose the name of the function over here. So just to go over this exercise, I'm going to basically create a data frame. So let's look at a data frame. So here this is a data frame has certain counts, let's say certain counts across calculated over 3 times a year. So let's say it is what you can say every 4 months in a year, we actually calculate certain parameters, maybe how much sales we have. So the first 1/4 is what 1/3 of the year is basically 5 sales. The next 1/3 is 7, and next 1/3 is 11. So this is particularly 3. You can say what do you say assessments or inventory after every 3 months. This is what the values are. In 2001, these were the sales, and 2002, these are the sales. So these are the certain values we have. Okay, so this is the data frame what we have right now. Now, what we want to do is, I'm going to, what I want to do is to want to group these values, basically group my values or aggregate my count values by years. So rather than having, right now they have like 3 values in a year, but I want to somehow look at the stats over the whole year. So what's the variance of sale was across the 3 in 2002, 2001, and 2002. So the function I'm going to use is ddply. So ddply is my input is a data frame. I'm trying to get an output as a data frame. I'm using the ply family function. D is the input data set, which is this data frame. I'm trying to group the values by year. So it's going to aggregate or basically group the values by year. So all the values which has the same year will be grouped together. And then I'm going to apply some sort of a function. So this is the function that actually works on it. So it's, I think, calculates, again, sort of, I don't know what CV stands for, but maybe a coefficient of variation. So CV, so I'm calculating the coefficient of variation across each year. So ddply, the first is data object, second, how I'm going to group, and the third is what function I'm going to apply. And that's essentially it. Runs, it groups it, and then essentially end up giving me this covariance. I could have used the same ddply function as ddply, and I can say the D, and then I want to group them by year. And let's say I want to find out the sum, how much sales, total sales were there across the year, the whole year. So then now what it does, it's basically it grouped the values by years and then sum them up, and oh wow, this is a bit different. Why it's saying sum is 6023. Oh, okay, sorry. Okay, some count. What happened? Some counts. No, it's count only. 1 second. Oh, okay. There's a function called summarize. It summarizes by counts. And now it counts. I think now it adds up the values and print it. So summarize is like you're trying to whatever. If I'm trying to aggregate the values by year wise, I have to say summarize. So summarize the function by basically summing up the counts. The previous function, what it was doing is only if I'm trying to basically execute a function of my own, and in that one I'm trying to take the values and then basically when I'm using the function here, I'm explicitly telling it that use only the count part of the data frame. Otherwise, it could have worked on everything over there. All right. So, oh, okay. So we are running ddply. So again, data frame input, data frame output on the data frame D. Grouping the values by year, we are summarizing the data, and the summarized statistics what we are using is the mean. So mean of the count by every year. So that's is going to return, and the next one is it's going to sum them up. Again, so we want summarizing the data by summary statistics. So what we are using is sum count, and this is going to be our column. The new after summary data that will be labeled as sum.count, and that's what the new label would be over there. You can also do some sort of what you call the transformation of data. To transform of a data is like adding one extra column based on certain stats. So here what we're doing is ddply. Again, input is data frame, output is data frame. This is input data object. So group the data by year. Transform is like basically add additional column with certain stats, and that additional is total counts. So, and the total count is replaced by sum of the counts when they're grouped by year. So essentially it summed up all the values by sale in a given year and provide against each of those entries. So it's not going, unlike summarize, which is provides only one three different values, it still returns you the original data frame, but against each year, it represents the total values as well. So sometimes you may need some as that kind of statistics to have it. Let's say if you want to calculate proportion of sales in a particular part of the year, so you need the total sales and the sales in that particular time zone. So you can divide one by the other and find out what proportion of sales were done in the first one third of the year, then second one third of the third, one third of the year, and so on and so forth. If you want to do like multiple ones, you want to have multiple columns that has to be added by adding some sort of a calculations. There's another function which is called mutate. So dplyr, the plier and dplyr are two packages which are really very good for doing, you can say, data frame based data analytics. Is really very useful functions they have. So here what we again are using the same function. This time I'm going to use same data frame aggregating by year. This time I'm mutating, and when I say mutating, I'm going to add multiple columns. So the first one is going to be the mean counts column. Then I'm going to calculate standard deviation and then possibly the coefficient of variation. And once I run this code, then the three additional columns are added to it. I can add one more column. Let's say this time I'm just trying to do a very custom check. I want to see basically in how many in case. So I want to find out the years in which the sale is greater than, let's say, the mean sale in the year is greater than 10. So again, the first few stats are exactly the same. The final one I'm just adding is I'm saying stats equals to mu, which is the mean is greater than 10. So if the mean of the sales is greater than 10, it's going to return true, otherwise going to return false. And then it just adds another column with false and true. So you basically, these ones can be used to, you can say, build an additional column to classify your data, which is available in data frame based on certain characteristics or based on certain parameters, which you would think in your analysis is really, really critical, or you want to group them based on those parameters. You can do that. Any questions here? Right. Okay. So sorry.
I have actually had a question about like status. Can you just repeat one more time, because I think I didn't understand clearly. Like status, like when is it false, when is it true? Last column.
Oh, this column over here.
Yeah. Mm-hmm.
Okay. So essentially, so when I'm saying mutating here, so these are essentially, you can add column whichever way you would like. So here I'm adding like mu, like in sense I'm adding mean and other things. That's because I want to look at the means. At the same time,
yeah. Okay, I see. Okay.
I just want to see if the mean is greater than 10. Let's say.
Yeah. Okay. Only when you specify. Okay, I see.
Yeah. Only if you specify, then only, it's not going to be. So what the key thing I want to convey is like this: if you have a data frame, you can like build classes, like you can have an if function here. So for example, I think so. Let me give you I can have the if function, and if else if or if else, I think, and you can say mu greater than 10. You can say, I think, a good sale. If it is true, it's a good sale, otherwise it's going to be a bad sale. So that's, now you classify your data based on certain filtration, right?
Yeah.
So so if you have like a big data set and want to group your genes, so this is a simple if else function, but you can have a really more complicated written to group your data in certain way. You can do it. And then once, let's say, bad and good, then I want to, let's say, aggregate. So once I have that one, I can save it in, let's say, another object, let's say D2. Okay. And now on this one, I can do apply, let's say I want to calculate okay, ddply, and I'm going to use is D2. That's the new data object. And I want to group the data by status. And then I basically want to, in a way, you can say summarize. Summary or summarize? So summary, I think, right? Yeah, summarize. And summarize, and I can just simply say mean, some name I want to give. So I'll say sales equals to sum, and sum of, what is the sum of mu? No, sum of counts. Count or counts?
Count, I think.
Yeah, okay. So now you can see, like, now I have built like two categories here, the bad and good sales. The bad sales were 23 total, and the good sales are 85. Just an example. But the idea is like, you basically can do a lot with using this particular function. Okay.
Thank you.
You're welcome. So let me clean it up. And so the next thing I'm going to talk about is like aggregates, and is again really very powerful one. You will see that when I start showing its utility, it's one of the really very nicely, you can do a lot of money with this particular function. And so before going that, so as possibly, I don't know that I mentioned previously, so for each of the package that generally develop, the good packages, they generally comes with a data set that help you to play with that particular package in order to develop your understanding with all the functions it has. And in their manual, generally use that a sample data set to tell you what commands are being used. So similarly, ggplot2, which is to build graphics, which we will start seeing from next week onwards, but it comes with its own data set called diamonds. And what it does, it has some information about diamonds, and based on that, you can do a lot of graphics. So, but right now, I just demonstrated the aggregate function. I'm going to use the same diamonds data set. So if in order to do that, first I have to load the library ggplot2. Once I load the library, forget about so these warnings are okay. I don't care as long as I don't get an error. And then I'm loading the diamonds data set. So I'm saying data diamonds. And now if I can say head diamonds, it tells me how the data in diamonds looks like. Okay, let me run it one more time. So these are the different, you can say, sort of attributes for the different diamonds. And if you look at how many data, how many observations are there, or how many diamonds has been characterized, approximately like 54,000 diamond information is there. And there are 10 columns, and then there is a caret value, there's a cut, there's a color, clarity, depth, table, and price, and basically then the dimensions of the particular diamond. The data type of caret is double, which is like integer values. Cut is an ordinal data, which these are categorical data, but there is an order to that particular categories. Same is a color is an ordinal. So some colors maybe have a much better price than some other kind of color. So they have a certain order associated with them. Same thing is with the clarity. So maybe more clear diamonds are more expensive. I have no information. I don't know about them much. So, but yeah, then we look at the depth. I don't know what this indicates, but maybe some sort of a parameter from there. Then there is a table, and then there's a price, which is integer values, and then there's the dimensions of each diamond. So about 54,000 diamond dimensions are over there. So before I start playing with any kind of data, the first thing I want to find out, I want to see whether the data is clean. Just to make sure that are there any NAs in my data set? So that's a really key thing to ask. So I can simply say is dot NA and diamonds. So I can check this one. So this will tell me, so for each position is going to, each basically value in the table is going to give me whether there is an NA or not. If there is no NA, it's going to give false. If there is an NA in the table, it's going to return me true. But the output of this right now for this function is going to be approximately 539,000 entries, a huge number. So I don't want to look at those ones. So simply what I do, I actually sum up my output of that one. So false is basically there is no NA. True basically it means it's an NA. And we know false is 0, NA is 1, false is 0, and true is 1. So if I add up all the trues, then I know how many NA values are there. So right now it's 0. So there is no NA value into it. So the data is really clean. So I don't have to worry about it. So now let's start playing a little bit with the aggregate one. So I would like to use the head diamond function just to have a view of the data set. And then we start running the aggregate function. Okay. So this is, so the way aggregate function is working is the function is aggregate and has basically 3 parameters in a way, if you can look at it. The first parameter is to tell how do you want to group the values. And once you group the values, basically once you have grouped the data on certain parameters, what value of those group thing you would like to see. Okay, what I mean to say is, let's say if you group our cut, if you group all the ideal diamonds and the premium diamonds separately, of all the grouped ideal kind of diamonds, which parameter or which part of the data you would like to do? You want to look at the mean price, or you want to look at the mean depth? What do you would like to see at that one? So that 2 things we have to specify. So essentially, after the tilde tells you how do you want to actually group the data. Here I want to group the data by cut. And what I want to look as output is in terms of price. Okay, I want to look the prices. And the data set I'm using is diamonds. And on the prices, I want to run a mean function. So for each of, once I group the data based on the cut, I want to find out of that particular cut, what is the mean price is. Does that make sense? Maybe now it does. Okay, so if it doesn't, let me know, I can explain again. But essentially what we have grouped the values, all the 59,000 or 54,000 observations by cut. So all the fair ones has put together, good has been put together, and then we have calculated a mean function over the price values, and these are the mean ones. So you can see that's really very powerful function. Similarly, we can also do is, let's say we are not only interested into cut, but we think the other really key property of the diamonds is the color. So we want to group our diamond data set both by cut and the color, and then we want to look at the mean price. We can do that as well. So now you can see that basically these are fair, good, very good, and ideal. These ones are of one particular color type. This is of another particular color type, and this is for another. So for each color type, it has then further categorized the cut type and then basically the price. All right. You can do the other way around if you switch this color and cut. So then basically what you see is then grouping will essentially happens with the fair, and then you see different color types. So just let's try that way. Now, if you see, basically all the fair diamonds are together and their different color prices are there. Here, actually, all the colors were together and their corresponding cut was different cuts were. So same data, but presented in 2 different ways. But the important thing here is like you can aggregate the values. You can aggregate your data based on certain parameters and can find out, calculate some statistics of some variable that corresponds to that particular data. All right. So we looked at one. Yeah, so this 2 properties we are looking over here. Okay, so now let me again get the head of the diamonds. Okay, so far what we saw was, okay, we are interested into price of if we group the data by cut. What if I'm also interested into, let's say, I also want to know carat about some information about the carats as well, not only the price but carats as well. So we can do that also. We can basically sort of use can perform a function on two different independent variables over here. So this is the function. So let me put that one and then we'll look at it. We are aggregate, but this time we are using two different properties to calculate mean over. One is the mean price and mean carat. Once we have grouped the data by cut. So once you've grouped the data, is going to calculate the mean of the carats and mean of the price. So, since these are two different independent, so the way to put them together is to use cbind function over here. Now, if you run it, the grouping is same as previously, but now we have the mean of both price and carat. We can do more complex ones here. So here, this is a little bit more complex version of the same one. Here, what we are doing is now we are grouping based on the cut, color, and clarity, these three different variables, and then basically finding out the mean price and mean carats. So again, it's going to be a pretty big table, but now you can see that they're grouped together based on three properties. So this is a cut, color, and then clarity. So you can aggregate your data in different ways, depending upon how you like to. All right. Yeah. Okay. So far we so then a little bit more complex again. This time we are going to do. So we are grouping the data by cut. Simplest thing is do group by cut. We are calculating, and we want to look at the price and carat. But this time we don't only want to look at the mean, we also want to look at the median of those values. So we are saying on each of these values, perform mean and median functions. So now what you can see is you can look at you can find the price mean, price median, carat mean, and carat median. So you can see that, and it's grouped by essentially the cut type, and it's really useful if you want to summarize your data in some way. And this was just to illustrate cutting. I just use the cut alone, but you can actually make it more complex. So you can basically have price, carat. You can group them based on cut and color, or maybe any other attribute. And you can find mean and median of price and carat, or some other variable. Not only two, you can have 5, 6, whatever you're looking for. Those values will be presented. So this is essentially, okay, it's a too big data set, but yeah, essentially you have price mean and price median and carat mean and carat median. So essentially that's the effective way you can actually end up using this aggregate function when you have your data frame and want to do a lot of manipulations and grouping of your data and want to build some stats corresponding to that particular group type. Any questions here? Cool. Right, there's no fun question. That's good. Okay. Now, this is the last part of today's one, and but I don't have a data to actually import it. I tried looking for it, could not find it. But essentially, this is a function called fread. That's from data.table package. So what is the use of fread? So sometimes your input CSV file could have really huge number of columns, and you don't want to import all of those columns. Sometimes it can take a longer time, or sometimes, let's say, your local machine is not really computationally that savvy, that it has too much amount of memory. You want to pick up only very few columns of that particular CSV file. A typical example I can give you is of single cell data. So in single cell data, you have genes, which like 25,000, 30,000 genes as rows. And in columns, you possibly have each individual cell or cell barcode. And those nowadays you can go up to like 50,000, 60,000, and 500,000 cells also you can do. So you can think about the CSV file, which is 500,000 rows, and then basically 20,000, 500,000 columns and 20,000 rows. It's a huge data set to import if you want to. So of that one, let's say if you want to import only very selective barcodes, let's say those barcode belongs to a very particular cluster type, and you have collected those barcodes, you can specify selectively only bring those columns which are corresponding to those particular barcode types, and then it will import only those ones. So let's say here I'm using fread function. This is input count.csv. So CSV files are specified that is separated by comma. And now this using the select argument, I'm trying to tell that irrespective of whatever number of columns are there in the CSV file, just import the columns whose headers are these three. Cell 1_1, cell 1_2, and so on. It's going to just import those selective columns to be available for me in R, and using that I can do whatever downstream analysis I would like to do. And in this case, I can avoid like creating objects of too big size. If you want to do some manipulation, it may take a long time. So why not just play with it while you're bringing the data in? So in that way, it's a memory effective and computationally effectively you can analyze your data. So this is pretty much what I thought of covering for today. If you have any questions, I am more than happy to answer.